Now we're going to move on to the different properties that alkanes have. And it really all depends on the quantity of carbons. For instance, between 1 and 4 carbons, these are typically gas at room temperature. From 5 to 8, they're liquids. Notice the word volatile here. That doesn't mean that they explode, although they could. It actually means they turn into gas very easily. And then finally, from 9 to 17, we're getting heavier. We're like talking about oils here and jet fuels. It all depends on the number of carbons. The more carbons there are, the heavier the compound is, the more effort it takes, the higher the temperature it takes in order to separate them from a solid liquid to a gas. 18 or more, so now we're getting into a lot of carbons, become more of a wax. For instance, the waxy coating on top of fruit that can make it so they don't mold as easily. They make it prettier so people want to buy it. They keep the moisture in better. These waxing coatings are alkanes with a lot of carbons. Once again, the bottom line you want to know is the more carbons, the heavier, which also means the higher the melting point. The higher the temperature it needs in order to do that. Alkanes in general are nonpolar. We talked about that before. Carbon and hydrogen are very close in electronegativity. Which means that there's really no attraction for for those electrons to go from one to another. There is no partially positive or partially negative. Does not exist for these compounds, which means that they will not dissolve in water. That means when we have an oil spill, for instance, we just had one recently a couple years ago in the Gulf, that oil tends to float on top because it's less stint and it's not mixing in with the water. And so it gets spread out in a very thin layer. And then they do mechanical processes or chemical processes to try to bring up that oil. It is flammable, and there was some discussion about setting it on fire to burn off the oil, but they realized that that would cause more pollution than the oil itself. And so they decided not to do that. Carbons have a very, very strong carbon-carbon bond. Very, very, very strong. So when it does burn, energy is released. When the carbon-carbon bond is broken, that energy that was keeping those atoms together is then released to its surroundings. And so alkanes, actually all organic compounds, not just alkanes, go through a combustion reaction, where we talked about this earlier in the semester, produces CO2 and H2O, always. This is called a complete combustion. You may have heard of carbon monoxide in households. That's caused by incomplete combustion. And that becomes dangerous. Whereas for complete combustion, having CO2 and water being produced, it's not as toxic. So if we look at this is an oil refinery. Remember, the greater amount of carbons means that it's heavier, which also means the heavier it is, the more heat it takes to boil it. So when we're looking at a refinery, a distillation, what they do is they separate it out by the boiling points. For instance, down here, oils takes a lot for those to boil, 350 to 450 degrees. Whereas if we're talking about natural gas like we use for our homes to heat our homes, it boils at a very low temperature, under 30 degrees. That's because this has fewer carbons. And this has many more carbons. So the heavier the more carbons, the heavier it is, the more it takes for it to boil. And that's how they separate these from the crude oil. So the number of carbons increase as we go down this chart. Also, the temperature then increases. So as the number of carbons go up, the temperature it takes to boil them goes up. So let's just do a review. We're going to do notice the word complete combustion of propane. Well, let's look at prop. Prop we already know means C3. So there's 3 carbons. Everything it needs to have 4 bonds for every carbon, and everything that's not a carbon has to be a hydrogen. So we're talking about C3, 1, 2, 3, 4, 5, 6, 7, 8, H8. That we learned in the previous section. For it to go through a combustion reaction, we have to react it with oxygen. And you're always going to produce CO2 and H2O. And some energy, but we're not going to need that for the balancing reagent part. So that's going to be our reaction. That's what we're going to want to balance. C3H8 plus oxygen yields CO2 and H2O. That means we have carbon, hydrogen, and oxygen here. We have 3 carbons on the left and 1 on the right. 8 hydrogens on the right, or on the left, 2 on the right. 2 oxygens on the left, 2 and 3. Another one from the water on the right. Notice that oxygen is in 2 different places on the right-hand side. Because of that, I'm going to leave it till the end. And I'm going to balance the carbons and hydrogens first. So I have 3 on the left for carbon. I'm going to put a 3 in front of CO2 to make those carbons balance. That changes our oxygens. We now have 3 times 2 here and 1 here. So 6 plus 1. We now have 7. We have 8 hydrogens on the right, or on the left, pardon. We need to make 8 on the right-hand side. So I'm going to multiply H2O by 4. Once again, that changed our oxygens. We still have 6 here. We now have 4 here. That means we have 10 oxygens on the right-hand side. We only have 2 on the left. If I multiply this by 5, that turns the oxygens into 2. So there's our balanced chemical equation. Alright, and that is all of section 5 or section 4. Next we're going to talk about functional groups.